We continue our talk on discrete Markov chains by looking at transition probability matrix. Transition probability matrix. We already saw transition matrix in the previous video, but here we want to give it a bit more attention. So transition probability matrix, a transition probability matrix or TPM describes the probabilities of moving between states in the Markov process. Let P be equal to Pij, like that, where Pij is equal to probability that next state is equal to J, given that the current state is equal to Y. That means the probability of moving from state I to state J, basically, right? So, in 16.2, we have some properties of the transition probability matrix. A matrix P is a valid transition matrix if, first of all, we have non-negative entries. So in the transition probability matrix, no entry must be negative. Very important. So uh, so no entry is negative. So we already know that probabilities are at max 1 and at min 0. So every probability you have should be from 0 to 1, not less than 0, not more than 1. Then rows sum to 1. So in the transition matrix, if you remember the last video, all the matrix for in a transition matrix, the values on a row add up to 1. So summation Pij over J is equal to 1. That's for the row. For the column, it may not be, but for the row, it has to be. So example, we have a weather model. I think we also looked at the weather model the other time in the last video, right? So we have a weather model here. So we have three possibilities. The weather can be sunny, cloudy, or rainy. And we have this transition matrix P. So you can see everything is between 0 and 1, from 0 to 1 if you like. So, but then across the rows, 0.7 plus 0.2 plus 0.1, that's 1.0. 0.3 plus 0.4, that's 0.7 plus 0.3, that's 1. 0.2 plus 0.4, that's 0.7 plus 0.3, that's 1 also. So, but of course, down the columns, it doesn't matter, but across the rows, it has to add up to 1. So, in essence, if you want to interpret this, like I said in the last video too, if today is sunny, 70% sunny tomorrow. So, if today is sunny, so this is like sunny, cloudy, rainy. So, if today is sunny, the probability that it will be sunny tomorrow will be 70%, that's 0.7. If today is sunny, the probability that it will be cloudy tomorrow is 20%. If today is sunny, the probability that it will be raining tomorrow is 10%. So everything adds up to 100%. So you can interpret like that. So of course, the next column talks about cloudy. So if today is cloudy, probability that tomorrow will be sunny is 0.3. Probability that tomorrow will be cloudy is 0.4. Probability that tomorrow will be rainy is 0.3. Then if today is rainy, the probability that tomorrow will be sunny is 0.2. If today is rainy, the probability that tomorrow will be cloudy is 0.5. If today is rainy, the probability that tomorrow will be rainy is 0.3. That's how you interpret all of that. Okay. So then we talk about the state vector. A state vector represents the probability distribution over states. So a state vector represents the probability distribution over states. So you have x of t at time t, you have x1, x2, x3. Those are three different states. So example, if you have the initial situation x of 0, 1, comma 0, 0, this means there's 100% probability of being sunny. So here you have x1, you have the probability of sunniness, if you like, is x1, then cloudiness is x2, and raininess is x3. So, but if you have an initial condition that there's 100% guarantee that it will be sunny, that's 1, like that. So that's the state vector. But then the state vector also evolves over time. So if you have an example like this now, so the state evolution, the next state is computed as xt plus 1. That's the next step. And that is equal to xt multiplied by p. So the previous state multiplied by the probability transition matrix will give you the current state. So imagine you have the initial state here. X of 0 is 1, 0, 0. Then it means that x1 will be x of 0p. So that means you have 1, 0, 0 multiplied by the transition matrix. And then you do the whole maths there. So interestingly, this will be 0.7 times 1, 0 times 0.3, 0 times 0.2. So all you have left is 0.7. So at the end of the day, because of these two zeros, now all these second and third rows will not be useful. So you just have 1 times 0.2, you have this, 1 times 0.1, you have this like this. So then we have Python code for a single step now. So if you run this, for one step, no, that's what we got right there. So if you're going to have another step, so it will not have to be that, x2 will now be x1 multiplied by p. So this x1 we got here now, we have to now multiply by the transition matrix again, and we keep going. So that takes us to the next step, talking about multiple step transitions. Okay, I think I'll do an example in the practice problems. So I'll just run through this and do an example. So if you go next step, so xn is x naught p raised power n. Okay, so that is after n steps now, you have xn to be x of 0 at p raised power n. Or if you like, this is xn plus 1 XNP. It still makes sense. So, but I'm going to demonstrate that in the practice problem. Then we have the steady state distribution. In fact, we're going to talk about that steady state distribution in the last video under discrete Markov chains in this playlist. Not like the last video, but the last video for Markov chain in particular, discrete Markov chains. So a steady state vector pi satisfies pi p equals pi. This means the distribution does not change over time. Okay, so for a distribution that doesn't change over time. So you can actually do a quick run. You have 1 over 3, 1 over 3, 1 over 3. But if you do that distribution, you end up getting something like 0.46, 0.3, 0.47, 0.33, and 0.21, like that. So then we have the absorbing state. We are going to talk about classification of states for a Markov chain in one of the videos to come. So a state is absorbing if probability that you move from I to I is 1. Of course, that makes sense. So the probability that if it rains today, it is going to rain tomorrow. That is an absorbing state. That means you're stuck with that rainy situation. So P is 1. So PII is 1. So that means you have that. If P22 is also 1, same thing happens. So here we say that state 1 is absorbing. So if this one was also 1, then we say state 2 is also absorbing. But here only state 1 is absorbing. So for both states to be absorbing, it means that uh we have this now. We have P1001. So you have 1, 2, 1, 2. So here both states 1 and 2, both states 1 and 2 are absorbing. Okay, both states are absorbing in that situation, because the probability that you move from state 1 to state 1 and probability you move from state 2 to state 2 are both 1. So they are both absorbing states. So we have an example here again. So uh, we have three states: loyal, neutral, loyal state, neutral state, and leaving state. That's LNE. Okay, so we then have this probability 0.8, 0.14, 0.05, and all that. So the initial condition is 0.5, 0.3, 0.2. So we can simulate that and we get something. So this is just talking about how a state evolves basically. So some key takeaways from all we've been saying: the transition probability matrix describes transitions between states. Each row sums to 1, like we've seen. Then future state is equal to current state times the matrix. Then long-term behavior talks about the steady state. That's where we have pi p equals pi, which we're going to still see in a future video. Then it is used in Markov chains and real-world systems. Then practice problems finally. Determine whether the following matrix is a valid transition probability matrix. Of course, what makes a transition probability matrix? Two things: no probability is negative. Every probability is from 0 to 1. None is below 0 and none is bigger than 1. So that condition is met. Then across the rows, everything adds to 1, right? So 0.5 plus 0.3, that's 0.6 plus 0.2, that's 1. 0.1, 0.6, that's 0.7 plus 0.3, that's 1. 0.2 plus 0.2, that is 0.4. 0.4 plus 0.5, that's 0.9. So this is not a transition probability matrix. So uncheck, that doesn't work. So check if this matrix is a TPM, the second one now. 0.4, 0.4, 0.4, that's 0.12. So it doesn't work. So that's not a transition probability matrix. Given this now, we have P. Given P equals 0.6, 0.4, 0.3, 0.7. Compute P squared, of course. That's about matrix. Let me quickly do that. 0.6, 0.3, right? 0.3, 0.6, 0.3. P is 0.6, 0.3, So this is 0 0.4, 0 0.7. So we need p squared. So p squared is simply multiplying the matrix by itself, 0 0.6, 0 0.4, 0 0.3, 0 0.7, also but multiplied by itself, right? So that is 0 0.6, 0 0.4, 0 0.3, 0 0.7. What do we do? I told you the Amorous method, if that's anything to go by. So you look at this determines how everything goes. So here you have two rows here rather. So you have two rows here. And because you have two rows here, you rewrite this in a particular way. You write each column twice. You have 0 0.6, 0 0.3, 0 0.6, 0 0.3. Then you come here, you have 0 0.4, 0 0.7, then 0 0.4, 0 0.7. Then having done that, then you now invert each row on each row like this. So 0 0.6, 0 0.4, and here 0 0.6, 0 0.4. Then down here, you have 0 0.3, 0 0.7. So that's 0 0.3, 0 0.7, then 0 0.3, 0 0.7. So you can then tidy this whole thing up. So you have this now to be uh you have this now to be equal to, so that is 0 0.6 times 0 0.6, that's 0 0.36 plus 0 0.12, that's 0 0.3 times 0 0.4. Then there's 0 0.4 times 0 0.6, that's 0 0.24 plus 0 0.28, that's 0 0.7 times 0 0.4. And 0 0.6 times 0 0.03, that is 0 0.18 plus 0 0.21. Okay. Then here you have 0 0.12 plus 0 0.49. So we can tidy all of that up and we see that p squared is equal to 0 0.36, and that's 0 0.48 there. Then here you have 0 0.52, 0 0.52, and down here we have 0 0.39, and here we have 1. That is 0 0.61, I think. Yep, that is 156, 0 0.61. So that is p squared right there. Then so here we have, okay, I think I can just take this once and for all. So let x naught be 1, 0, and then we have p to be 0 0.2, 0 0.2, 0 0.5, 0 0.5. Then using the same problem, we want to compute x2. So I'll just do this in 2 steps, and that'll be it. So we have x naught is 1, 0, then 0 0.8, 0 0.5. So x naught is 1, 0, x naught is 1, 0, and then we have p to be 0 0.8, 0 0.5 here, that's 0 0.2 here, 0 0.5 here. So we now need x1. So we know generally, right? Generally, we know that xn plus 1 is equal to xn multiplied by p, you know? That's xn multiplied by p. So that means that x1, which we need now, okay, so we need x1, and x2, in fact. So we need this. Okay, let me not just make it a side note. Let's just make it an integral part of this. So I can say to compute x1 and x2, we start like this, that we know that xn plus 1 is equal to xn multiplied by p. All right. So x1 will be, so x1 would be x0 multiplied by p. X0 multiplied by p. And what is x0? That's 1, 0, 1, 0. So this is, so x1 now is 1, 0 multiplied by p, which is 0 0.8, 0 0.8, 0 0.2, 0 0.5, 0 0.5. Okay, and because this is only one column, only one row rather, what do? We write each of the columns there once. So that means x1 is equal to 0 0.8, 0 0.5, then 0 0.2, 0 0.5, and then we put this row over them. That's 1 0 1 0. So, and of course, because we are multiplying a 1 by 2 matrix by a 2 by 2 matrix, so if we bring this out, we get a 1 by 2 matrix again. So very important to note that. So now x1 is equal to 0 0.8 times 1, that's 0 0.8, 0 0.5 times 0, gone. Then 0 0.2 times 1, that's 0 0.2. So that 1 is still retained there. So that's that. So we then go ahead and say for x, for x2, we have x1 multiplied by p still. So that means that our x2 will be, so x1 now is 0 0.8, 0 0.2. We have 0 0.8, 0 0.2, and p remains 0 0.8, 0 0.2 like that. So p is 0 0.8, 0 0.2, then 0 0.5, 0 0.5. So that we then have so write this once. So you have 0 0.8, 0 0.5, 0 0.2, 0 0.5. Then bring this over them. So that is 0 0.8, 0 0.2, then 0 0.8, 0 0.2 all together. So then we have x2 equals, so this is 0 0.2 times 0 0.8, that's 0 0.64. That's 0 0.64, 0 0.64 plus 0 0.10, yeah? That is 0 0.10 plus, okay, no. Then this now is 0 0.2 times 0 0.9, that's 0 0.16 plus 0 0.10 still. That's 10, two decimal places. So that means that x2 is equal to, if you add this together, that's 0 0.74, and this is 0 0.3, 0 0.26. So if you add the two together, it will still be 1. So this is x2 right there. Okay. So with that in place, then we can move on from that. So we've answered questions 5 and 6. So try your hands on other questions and let's see how well you get the gist. So with this, I come to the end of this interesting video on transition probability matrix, TPM. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. So if you have subscribed already, I thank you very much for doing that. And if you have not subscribed, go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join, which gives you special privileges like getting to see some videos first before others, or being the only one to see certain videos, you know, and we can build this community together. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.